cosmology using high-Z supernovae, and I think that was work that she did while she was a graduate student. But she's most known for participating in large and leading large surveys, including the Deep 2, Aegis, Primus, and MOSDEF. One of the highlights of Alison's work is one of the co-discoverers of the main sequence of galaxies, which has had a huge impact on our understanding of how galaxies form and then evolve as they decrease in star formation. One of the main results from that was showing that individual galaxies themselves are slowing down in their star formation rates over time due to gas exhaustion and other processes. She's also an expert on winds and feedback in galaxies. And today she's going to talk about this. I think I know what you're going to talk about. It's this one really cool object that has an enormous galactic wind, which was, I think, published in Nature not too long ago. So with that, Alison, take it away. Thanks for being here.
Thank you. Well, thank you for inviting me. Sorry that we're having to do this online, but we will do our best. I tried to put together a fun talk for you all. So yeah, I'm going to talk about this single galaxy, which is most of my career I've done statistical studies. So it's really odd for me to spend an entire talk talking about one galaxy. So what I'm going to do is the second half of the talk, I'm going to focus on this one source. And then the first part, I'm going to give you some general introduction and then talk about a population of galaxies that we've been studying from which we found this particular source. So let me see how I can make this work. Sorry, making Zoom and Keynote work together is a little tricky. That's not working. There we go. Okay, so just to remind everybody, we still haven't solved the missing baryons problem. So we know that about 5% of the local universe mass energy density should be baryons, but we have not actually found all of them. And we know what that fraction is really well from CMB observations and other cosmological observations. But when we go and look and count up the baryons that we can see in stars and gas and dust and galaxies, we only see roughly half of them. So it turns out that many baryons are around and in between galaxies in what we call the circumgalactic medium and the intergalactic medium. So if you guys can see my cursor here, this is my super fancy schematic of galaxies where the green is showing you the circumgalactic medium, so the gas that's around galaxies, and then the blue is the intergalactic medium, or the gas that's in between galaxies. It's really hard to observationally detect this gas because it's very low density, and it's multiple phases with different temperatures and densities. So in simulations, people are much more familiar with seeing this. So this is just a snapshot of a simulation with the stars and galaxies and then the gas. And you tend to see the gas, spread out through the entire volume. It's that larger scale gas that we're talking about. So it's easy to see in simulations. It's really hard to actually observe with telescopes. Focusing on the circumgalactic medium, or the CGM, that's the gas that's surrounding galaxies, that's outside the disk and the interstellar medium of the galaxy, but still inside the virial radius of the dark matter halo. So it's gas that's very much part of the galaxy, but it's a larger scale than what we're used to thinking of. And the CGM is the reservoir of gas that's needed to fuel future star formation. There's not enough gas in the disk of galaxies to keep them forming stars at the rate and the timescales that we observe. So some of that gas in the CGM has to be fueling the future star formation. It's also where we think, the scales where we think galactic gas recycling happens. So we know that the CGM is massive and enriched and multi-phase. So how do we know these things if we can't see it? So typically the way that it's observed is we probe the CGM through absorption sightlines that happen to exist to background quasars. So the idea is that here's the observer with your telescope. There happens to be some distant quasar that there's a galaxy along the line of sight that's near enough to the sightline that you probe the halo and the CGM of that galaxy. And then you can see that gas in absorption in the quasar light. So at a lower redshift than the quasar. you see absorption features, and then you can see that there's a galaxy at that redshift near the quasar. So we only can see it this way in absorption, and you can't choose the foreground galaxy. You just happen to have some galaxy that happens to be near the line of sight to a quasar. And then you can only get one sight line per galaxy, and it just happens to be at whatever distance from the galaxy that it is. So you don't have a lot of control over these kinds of studies. This is a slide from the COS Halo survey. And from doing this over tens of quasar sightlines and different galaxies, they were able to determine that the CGM is massive and enriched. So we can statistically build up a picture of what, sorry, the garbage truck is going to come by. It might be loud for a second. Statistically, we can build up a picture of what the CGM has to look like on average for galaxies. So we just get a statistical picture here where we have different sight lines at different distances for different galaxies. And from this, we know that there's a lot of mass in the CGM, actually more than the mass that's in the stars, the gas, and the dust in the disk or the disks of galaxies. But again, this is inferred statistically through looking at a single sight line across many, many different galaxies. And so in this schematic here, this is just a cartoon. We have no morphological information. We just have random sight lines at different distances through different galaxies. Okay, so in terms of where does this CGM come from? Theory points to it being created in two ways. One is through infalling gas from the cosmic web and the IGM, so gas from larger scales flowing onto galaxies due to gravity. And then also outflowing gas from the galaxies themselves. This is a really common cartoon picture that everybody shows when they talk about the CGM. So here's an artist's rendition of what we think is going on. So the galaxy disk is here at the center, and then you have accreting gas coming in from the cosmic web, and then you also have gas outflows and recycled gas being ejected from the galaxy onto large scales. This is just a picture of what may be going on. We can't actually see the infalling gas or the outflowing gas directly for very many galaxies. So like I was saying, observationally, we have this statistical knowledge of what the CGM has to look like by detecting it in absorption across different halos and different sight lines to different galaxies. And with that, you don't have the kinematic information about how the gas is moving relative to the galaxy. You don't know for any individual galaxy, when you look through the quasar sightline through the halo, you detect gas and absorption, but you don't know if it's inflowing or outflowing because you don't know if it's on the near or far side of the galaxy. So you lack kinematic information, and then you also lack morphological information. So while we know a lot about the CGM through absorption studies, we can't really test this cartoon picture right here because we don't have the kinematic information or the morphological information. So a large part of what informs that previous cartoon picture is studies of very nearby starburst galaxies where we can actually see the outflows in emission. So this is M82. This is a very nearby starburst galaxy. This is an optical image. It's an edge-on disk. If you then go and look at infrared and X-ray wavelengths, this is the optical disk in green. You see this huge bipolar outflow where you're seeing warm dust and hot gas being ejected from the galaxy with this sort of bipolar outflow with a large opening angle on same scales or similar scales as the galactic disk. So this kind of data provides much of the motivation for that previous cartoon that I was showing. M82 is a starburst galaxy, and the idea is that it's the starburst itself and the supernovae that are driving the gas out of the galaxy. This is the closest starburst galaxy to the Milky Way, though. And it's in particular, it's 11 million light years away, and the redshift is 0.0007. So most galaxies are at higher redshift. We can't see outflows in emission like this for very many galaxies, because there's just way too low surface brightness. It's only for the most nearby sources that you can actually see the outflows in emission like this. So while this data is amazing, it just doesn't exist for very many galaxies. So what we do for more distant galaxies, the way that you can detect inflows and outflows specifically towards more distant galaxies is using what's called down the barrel observations. So instead of having a sight line through the halo where you're using a background quasar to illuminate a skewer through the halo, here's your observer with your telescope. You point directly at the galaxy itself and you probe gas on the near side of the galaxy. And if you see that there is gas that's redshifted relative to the stars and the gas in the galaxy, then you know that there's inflowing gas. You're detecting inflows. Conversely, if you see blue shifted gas relative to the gas and stars in the galaxy, then you're seeing outflowing gas. You don't see gas on the opposite side of the galaxy because the galaxy is in the way. So this is the main way that we've detected outflows and a handful of inflows towards high redshift galaxies. So in this way, you can get kinematic information, but you still don't have morphological information because you're just looking at a sight line towards the center of the galaxy. But this is how we know a lot about inflows and outflows of high redshift galaxies. Okay, so that was a bit of background. Let's check time. Great. Okay, so now I want to shift to talking about this really interesting population of galaxies that we've been studying. So I'm going to take you through a bit of a history of when these galaxies were discovered and what we've learned about them over time. So the story starts in 2007, which is now feels like a very long time ago. I was a postdoc. Some of you were probably in high school or younger. And there was this really interesting paper by Christy Tremonti, who was a postdoc at University of Arizona at the time, and two grad students, Alex Simon-Stanek and John Moustakis, both at University of Arizona. And they found what they thought were post-starburst galaxies at redshifts of about 0.6 with these really, really extreme outflowing winds. So what these were discovered in Sloan, but not in the Sloan Galaxy Survey. They were discovered in the Sloan Quasar Survey. So they were very small, very bright, and very blue. So in imaging, they thought that they were quasars. And then they took spectra and it turned out that they were galaxies. And they had what looked like post-starburst absorption features in their optical spectra. So what that means specifically is they saw Balmer features from A stars. So there had been a burst of star formation in the not too distant past, and it didn't look like there was much ongoing star formation. And that was from the oxygen 2 doublet, which is an emission line that when it's bright, it indicates that there's a lot of ongoing star formation. And these didn't have much O2. So they looked like really typical post-starburst spectra, except they had these really, really fast outflows seen in the magnesium 2 absorption line, which is a common ISM line, which is often used to detect outflows. But they saw outflows that were 2,000 kilometers per second. Most galactic winds are about 200 kilometers per second. So this was like an order of magnitude higher. Okay, so that's when the story starts. This is from their original paper, the discovery paper. So these are different galaxies here, and then this is a zoom in showing. So here you can see the post-starburst features, the absorption features, and then there's very little O2. And then this is the magnesium 2 absorption line over here, and then this is a zoom in on the right. This is a doublet, this magnesium 2 absorption. And so the dashed line here is showing you the systemic redshift of the galaxy. So normally you would just see 2 absorption lines at those dashed lines. And what you can see instead is that they're blue shifted by 1,000 to 2,000 kilometers per second. These profiles can sometimes be pretty complex with multiple absorption features. And often they don't have much absorption at the systemic redshift, which is very odd For distant galaxies, when we see outflows, we tend to see absorption at the redshift of the galaxy, and then we see a wing out to higher velocities. And here, often you don't even see any absorption at the redshift of the galaxy. So it looks, at least in some of these cases, like there was like a very distinct event. I remember when I saw these spectra, I thought, oh, it's like a bomb went off and ejected all of this gas from the galaxy. And it wasn't even clear that there was still gas in the galaxy anymore. Anyway, so this paper was really exciting when it came out. So I joined the team a few years later because both of those people who were grad students then came to UCSD to be postdocs in my group. And we got a bunch more data on these galaxies. So this is showing you HST data. We wanted to see the sizes and the morphologies. So we targeted the ones that had the youngest stellar ages. So the ones that looked like they had had the starburst most recently. And what you can see from looking at the HST images is two things. A lot of the light is centered just at the very center, and there's a really, really compact core of light. And then you can often see tidal features. They look like fairly late stage major mergers. Some of them are a little bit earlier stage, but a lot of them look like late stage major mergers with tidal tails. And we also found when we measured the light profiles that they're really, really small. So, so now I've changed the title to compact post-starburst galaxies at redshift 0.6 with extreme winds. And these galaxies are very massive. They have stellar masses around 10 to the 10.5 to 10 to the 11. So definitely above the break in the stellar mass function. They have these late stage major merger morphologies, and they're very compact. So the effective radii are typically a few hundred parsecs. Most galaxies have effective radii of like 5 to 10 kiloparsecs. So these are extremely compact, which raises the question of, is that light coming from an AGN? So we looked at that, and we can't find AGN in them. At least it's not obvious. So very few of them have the magnesium 2 broad emission lines that you often see from AGN. We looked at emission line, optical emission line ratio diagnostics. Don't generally look like AGN. We got Chandra data to look for X-rays. We have a few detections, but they're consistent with the level of star formation that we know is in those galaxies. So the X-ray data does not point to there being an AGN. A handful have detections of this neon 5 line, which is often associated with AGN, but it turns out you can also get that from shocks, particularly fast shocks. And we know that these galaxies have 2,000 kilometer per second outflows, which can definitely give you that line. So it's not clear that they have AGN. We looked really hard. This is showing a plot of the outflow velocity versus the effective radius. So here you can see how tiny these things are. They're like 0.2 kiloparsecs. And then we also looked to see if there's a correlation between the outflow velocity and the neon 5 luminosity, the mission line luminosity. Generally for AGN-driven outflows, there is a correlation between the AGN luminosity and the outflow velocity, and we did not see that. So they don't appear to have strong AGN, and it does not appear that the outflows are correlated with this neon 5 line. Okay, so then we also realized, we looked at the WISE data, which is this all sky infrared survey, and half of our galaxies were detected in WISE, which means that they're not post starbursts. It means that they're starbursts, that they have really high star formation rates. You can't see the galaxies at these redshifts in WISE unless they're forming a lot of stars, which is then heating up the dust that you're getting the infrared emission from. So this is showing SEDs for 3 different sources. These are their morphologies. These are the WISE points, and their best fit with the blue line here is a starburst SED. So we realized these aren't post starbursts, at least half of them are starbursts. And they have star formation rates that are very high, like roughly 200 solar masses per year, which at redshift of a half is high. Okay, so We learned that they're compact, very compact. They don't have AGN that we can find, and they're forming stars at a really high rate. So then if you make a plot of, this is the star formation rate surface density. So how compact of an area the star formation rate is coming from at the center of the galaxy versus stellar mass. The contours here are, the red contours are showing star forming galaxies at redshift 1. And the outer contour is the 99.7% level. And then the orange are ULERGs, so gas-rich mergers at redshifts less than 0.3. And then the black are R sources. So you can see that they're high mass, around 10 to the 11. And they have really extreme high star formation rate surface densities. And some of them are already go all the way up to or close to the Eddington limit, which is insane. Galaxies don't tend to have Eddington limited starbursts. So we realized that they're not just starbursts, they're like these extremely compact starbursts that appear to be approaching Eddington limit. So very extreme sources. Okay, so getting back to this idea of how can these galaxies have these 2,000 kilometer per second winds? When they were first discovered in 2007, when they wrote that paper, they just said, well, they must be AGN driven because there weren't any galaxies that had outflows that fast that weren't from AGN. So even though they knew they didn't see AGN in them, they said, well, maybe there was an AGN and we just don't see it anymore. They couldn't really explain why, but they were like, it has to be an AGN. But it turns out you can produce a really fast outflow from stellar processes if the galaxy has the properties like the ones that I'm showing you. So there's two ways you can do this. One is radiation pressure, basically photons pushing on dust grains. And then the other is thermal energy from supernovae. And for radiation pressure, theoretical work indicates that radiation pressure can eject gas to velocities similar to the escape velocity for the galaxy. So if the galaxy happens to be both massive and compact, then it will have a large escape velocity. And for the supernovae, if you have both a high star formation rate and a small launch radius, meaning that it's a very compact star formation, like high star formation rate surface density, then you can also get a fast wind. So if you plug in the numbers, basically you can get roughly a 2,000 kilometer per second outflow from stellar processes alone if you have a compact, massive starburst galaxy, which these are. So it seems possible for these sources to drive these extreme winds without invoking AGN that we don't see because of their compactness and their high star formation rate surface densities. So just to show a little bit more of the other kinds of data we've been gathering, we've been looking for molecular gas in the galaxies and in the outflows. This is just one source here showing we have data from both IRAM and ALMA telescopes. This is showing, I think, ALMA data for one source. So this ochre color, which is kind of a gross color, that's the CO. This is velocity here. So that's the systemic velocity. So this is the molecular gas in the galaxy. And then there's this wing that goes out to around 1,000 kilometers per second of blue shifted outflowing gas. And overlaid are the contours from the same source for different lines, both in emission and absorption. And you can see that they all probe roughly the same high velocities. So in general, we found that there are very large amounts of molecular gas in these outflows. For this source, about 35% of the total molecular gas in the system is in the outflow itself, which is a pretty high fraction. Sometimes the outflows are spatially extended up to 10 kiloparsecs, which is far. And like you can see here, they can have really high velocities of around 1,000 kilometers per second. And if you look at how much molecular gas there is in the galaxy and you look at the star formation rate, like how quickly the galaxy is using up the gas, you find that you infer very short depletion times, like tens of millions of years. Basically, the star formation rates are so high that these galaxies are going to quench. They're going to stop forming stars pretty soon, if they haven't already. This is another data set.
What are the gas masses you're finding? Sorry to interrupt.
Oh,
what are the masses? Must be around 10 to the 9 if the depletion.
I was going to say 10 to the 9. I think that's roughly right. Yeah.
Okay. Thanks.
There's these 3 papers by Jim Geach that give the details of the individual sources. I think it's roughly 10 to the 9.
Okay, thanks.
Yep. This is showing data of the rest frame optical emission lines. So this is data from NERSPEC at Keck and Sloan and MMT, showing the suite of rest frame lines from O2 to S2, and then each row here is a different galaxy. We got the NERSPEC data because we wanted to look at H alpha, because we wanted to look at star formation rates. But what we noticed unexpectedly was, you can see we often find when we do the emission line fitting, there's often this additional, in pink here, a blue shifted broader component. That is the signature of outflowing gas in emission. It's very common to see that in galaxies that have outflows. So typically it looks sort of like this. Like in Sloan, it's very common to see these sort of blue shifted, like small wings, but occasionally we saw these really large wings in terms of the amount of flux. And you can see in this source, the outflow is really strong. We also then could compare the kinematics of the outflows in emission with the outflows in absorption for the same galaxies. So this is from a paper in prep that Serena Perota, who's a postdoc here at UCSD, is leading. This is just showing for 4 different sources the emission line. This is a velocity space, showing the width of the emission lines and then the absorption lines. And you can see that the maximum velocity is very similar, both in emission and absorption. It's very rare to have data like this for the same source, where you're seeing the outflow both in emission and absorption. So we have very detailed kinematic information for the outflows, but we are still lacking morphological information. Okay, so now I want to talk about this one source, J2118. So this is one of the galaxies in our sample. It's at a redshift of a little less than a half. Stellar mass is a little greater than 10 to the 11, has a star formation rate of around 150 solar masses per year. So a very typical galaxy in our sample. This is the HST image. It's showing this really highly peaked stellar core. The radius here is only 400 parsecs. And then these large or larger tidal tails. So the half-light radius is about 2.5 kiloparsecs, but most of the light is in this little tiny core right here. This is showing the optical spectrum. So you can see the Balmer absorption features here. This is oxygen 2, so it had a little more oxygen 2 than most of the galaxies in our sample. And then we didn't actually see any magnesium 2 absorption for this source. So we didn't know if it had a wind. Roughly, I think 1/3 of the original sample did not have magnesium 2 absorption. So the assumption there is that the outflows are somewhat collimated. They're not completely isotropic. So sometimes if the outflow happens to be more across the line of sight than along the line of sight, then you won't detect it in absorption. So for this one, it wasn't clear initially if it either didn't have a wind or if it just had a wind that was more across the line of sight. This is what we saw when we were looking at the NERSPEC data. And in particular, the thing that really jumped out to me was this. This is the oxygen 3 doublet, the 5007 line, and it's really broad. So the outflow, the flux in the outflow is really strong, particularly compared to the flux in the gas that's still in the galaxy, in the ISM of the galaxy. This is from Sloan, the O3, so it's a little ratty. The signal to noise is not great, but you can see that it's very broad. And I remember when I looked at that, I thought, that's so weird. Like, I've looked at a lot of galaxy spectra and I'm used to seeing outflows and they don't usually look like that. It was just really broad. So I sort of had that in the back of my mind that this was a source that I was curious about. So we applied, so we were basically using every telescope we could think of to try to get more data on these galaxies to understand what was going on with them. And there was this new instrument at Keck called KCWI, or the Keck Cosmic Web Imager. It's an IFU, so you get a spectrum at every pixel on the sky. And it was designed to be sensitive to very low surface brightness emission, particularly at blue wavelengths. The idea was to image the cosmic web in emission. Started taking data in 2018 in shared risk mode, and I think normal operations started in fall of 2018. So we put in a proposal to look at our galaxies, and we were turned down by the TAC. I think it was the first and maybe only Keck proposal I've ever had that was rejected. And they said, this is going to be ground-based seeing. It's not behind an AO system. Why do you think that you're going to see anything? Like, why do you think that the outflow will be so physically extended, like beyond the galaxy, that you would see it? So we didn't get the time. I did get time on KCWI to look at low redshift AGN outflows, which had already been discovered. And so we already knew that we would see something. And we were trying to get better data. And we had this one run in November of 2018, where it was like this beautiful night. It was 0.7 arc-second seeing, totally clear. It turns out KCWI is so sensitive that we were just banging through our sources. Like 1 hour per object was enough that we did like 10 galaxies, or yeah, something like 10 galaxies or 8 galaxies in a night. And at the end of the night, I thought, I want to steal 1 hour and go look at one of these intermediate redshift starburst galaxies. And in particular, I wanted to look at that one that had the really broad O3 because it was just so strange. I was really curious about that broad O3, and it happened to be up at the end of the night. So we stole 40 minutes and we went and looked at that source. And I think this is a really good example of an anecdote of like maybe why Q scheduled observing is not always the greatest way to go. Like this was definitely something where I just sort of stole the time from myself. So anyway, we went and looked at J2118. So this is now zoomed out. So here's the galaxy at the center. I've stretched this really hard so that you can see the tidal features, but again, the bulk of the light is right here at the very center. And you can see that there are no other galaxies nearby. And so here's what we saw with KCWI. We saw this huge oxygen 2 nebula. Like it's huge. And it's centered right on the galaxy. So one of the first things we did was change the name of the source from J2118 to Makani, which is wind in Hawaiian. So this is 100. So this is just showing oxygen 2. KCWI only has the blue arm built. The red arm is still being built right now. So we didn't have like oxygen 3. But in oxygen 2, we saw this 100 kiloparsec nebula, coherent structure with 40 minutes of time on KCWI. And again, the reason we can see, so for observers here, the surface brightness is getting below 10 to the minus 17 in 40 minutes, which is just nuts. So this little tiny circle here is showing you the extent of the starburst. And then again, I stretched the black really hard so you can see the tidal features. So the galaxy itself, the scale is like, you know, between 10 to 100 times smaller than this oxygen 2 nebula. So this is one of the largest O2 nebulae that's ever been observed, and it's the largest individual galactic outflow ever observed, at least that I am aware of. So because KCWI is an IFU, we have more than just the morphological information. We have, oh, sorry, let me just briefly mention the morphology is really interesting. Like these holes immediately reminded us of this sort of classic hourglass limb brightened bipolar bubble type shape that you see in nearby starburst galaxies. So here's M82. This is showing you the dust. And then this is another nearby galaxy, NGC 1482, which again has this sort of evacuated bubble. It's like an expanding bipolar bubble um, that's perpendicular to the disk that you see for nearby galaxies. But the scale here for both of these, the outflow is the same scale as the galactic disk, right? So it's like a few kiloparsecs. Whereas here, there's not a disk, but the galaxy, you know, is like this big. So here, the outflow is an order of magnitude or more larger. And because this is an IFU, we have kinematic information. So this is showing the maximum blue shifted velocity. So the maximum outflow velocity at every pixel for this nebula. So that the galaxy is here in the center. And the scale here is going from 0 to minus 2,000 kilometers per second. So you can sort of see visually right away that there's sort of two distinct features here. There's this larger scale, slower outflow. It's about 300 kilometers per second. And then the dark blue here is a smaller scale, like 20 kiloparsecs. So it's still very large scale, but it's not the 50 kiloparsec scale, the large one. So this smaller scale, faster outflow that goes, the fastest velocities are approaching 2,000 kilometers per second. And the typical velocity is around 1,800 kilometers per second. This is what the full 3D data set looks like. So we took it and rotated it. And one of our colleagues, Jim Geach, is at University of Hertfordshire, where they had a group there that works on really nice pictures of data realizations. So it's rotated here. And the third dimension here is velocity. It's not distance. We don't have distance. We just have velocity. So this is the bluest here is minus 2,100 kilometers per second, and the reddest is plus 700. So it's redshifted 700 kilometers per second. So here, this smaller scale, faster outflow is easily distinguished from this larger scale, slower outflow. Okay, again, this is not the actual 3D morphology. If anything, my guess is that the 3D morphology is inverted from this, that the fastest gas is on smaller scales and the slower gas is actually on larger scales. Okay, so this is where this gets really cool. So this galaxy, we have this really nice spectrum of the host galaxy and the stellar population. So you can do stellar population fitting and fit the star formation history of the galaxy from the spectrum, from the continuum part of the spectrum. And so the black here is the optical spectrum, and then the pink is a fit to the continuum. And then these colored lines are showing you the contributions from different ages of stars. So this galaxy had 2 starburst events, and we can date them. So the most recent one is less than 7 million years ago. And then before that, there was another starburst episode at 0.4 gigayears ago. And then there's a little bit of light from an older stellar population. That's like 8 gigayears. And you can see that both of these more recent starburst events are contributing to this overall Balmer absorption, but it's the more recent one that contributes the really blue light. Okay, so there was 2 recent starbursts, one about 7 million years and one about 0.4 gigayears. So now if you go back and look at the kinematics, this is a map now here. Instead of showing you the maximum outflow velocity, I'm showing the sigma or the width, but it's very similar. You can see that this is the larger, slower outflow that we've outlined in yellow here, and then the smaller scale, faster outflow outlined in red. So we started calling these episode 1 for the larger one and episode 2 for the smaller one, because if you take those 2 starburst episodes and you look at the sizes and the speeds of these outflows, it all fits together that they could have been driven by those starburst episodes. So to walk you through this, for that more recent starburst, that happened 400 million years ago, gas that's moving at about 120 kilometers per second, if it was ejected 400 million years ago, would now have reached scales of about 50 kiloparsecs, which matches the kinematics and the scale of this larger outflow. So we started calling that episode 1. And then the sorry, that was the older starburst. The more recent starburst, which was 7 million years ago, gas moving at 1400 kilometers per second would have reached 10 kiloparsecs, which roughly matches the scale and the kinematics of the faster, smaller outflow. So basically the speeds and the sizes of these two outflows that we see in this galaxy are consistent with being driven by the two known starburst episodes and when they happened, which is pretty cool. This slide's a little complicated. This is just to show that on the smaller scales, when you zoom into and by smaller scales, I mean 20 kiloparsecs, it's still really large scales. We have different tracers of the gas. We can see molecular gas, neutral gas, and ionized gas. And we can compare, these are just comparing their morphologies in different velocity ranges. So this is showing around systemic, this is showing the green is the molecular gas and CO, and then the colors are the magnesium-2 emission. And you can see that they have very similar morphologies. And again, this is comparing the oxygen-2 emission to the CO. And then the bottom right is showing the really fast gas. So this is at like minus 1,000 kilometers per second. This is the CO and the oxygen-2. So the point here is just that we can see these outflows, especially the smaller scale, faster one, in different phases and compare the kinematics and spatial extents. And they seem to match pretty well. Okay, so getting back to the mass. So it's really important to understand how much mass is in these outflows in order to understand how impactful the outflows are in terms of the future evolution of the galaxy. Basically, you want to know how much mass is being removed from the galaxy to know how it's going to impact the future star formation rate of the galaxy, and whether like these outflows are dramatic enough to quench star formation. So we only have oxygen-2 in emission for both the outflows from the KCWI data. So we started trying to derive the outflow mass from the oxygen-2, and then it's so uncertain. Once we got to like 2 orders of magnitude uncertainty, I was like, we're not doing this. This is way too uncertain. So we went back to our long slit H alpha and H beta data, and we were able to estimate ionized gas masses in the outflow of about 6 times 10 to the 8 solar masses, but that's fairly uncertain. The CO molecular gas in the inner 10 kiloparsecs is around 10 to the 9 in the very fast outflow, and it's 4 times larger than that at lower velocities, so at the systemic velocities of the galaxy. The mass outflow rate for molecular gas in the episode 2 wind, so that's the smaller, faster outflow, is about 250 solar masses per year, which is roughly 2 times the star formation rate. That's really high. Basically, that fast wind is ejecting a lot of mass from the galaxy, definitely enough to impact the future star formation rate and potentially to quench the galaxy. And that high rate is consistent with the molecular outflow rates for other compact starburst mergers, basically ULERGs at redshifts greater than 1/2. So the smaller, faster wind has a really high mass outflow rate. I actually think the best estimate of the outflow mass might come from theoretical work. So there's this paper from 2018 from Cassandra Locus, where they model how the circumgalactic medium could be created from outflowing winds and bubbles that move out to very large scales. And in this model, for a galaxy that has a star formation rate of around 100 solar masses per year and a mass of 10 to the 11, so similar to this galaxy, they find that supernova-driven winds that have an initial velocity of around 1,000 kilometers per second, there's like successive shells, and the mass in the shell at 10 kiloparsecs is around 10 to the 9, and it has a time scale and velocity that match our observations. And then the mass in a shell at 100 kiloparsecs is 10 to the 10. And again, with a time scale and a velocity that match our observations. So this paper points to there being really substantial amounts of mass in these outflows. And these new KCWI data are also relevant for this longstanding problem of how cold gas can even exist at such large distances from galaxies. So, people have known for a while that you can see, for example, magnesium 2 absorption showing outflows at really high velocities. And theorists have been trying to work on how that can exist, because historically, when people have run simulations of cold gas being ejected from a galaxy into a hot halo, it usually got stripped and basically disintegrated, like it got ripped apart. So they couldn't keep cold clumps of gas moving at high velocities to large distances from the galaxy. But in the last few years, there have been several papers that have made a lot of progress on this. So this is just one example from Max Gronke and Peng O, showing they have a cold cloud that gets ejected through a hot medium, so like a hot halo. And they found that mixing of the hot halo gas with the cold gas in the outflow can actually create and sort of condense, I think, new cold gas out in the halo. So cold gas can get created in situ at large scales in the halo due to the entrainment of the wind. And another example, this is work from Evan Schneider and Brant Robertson and Todd Thompson of a simulation using the Seagull simulation. They're trying to study whether cold gas like 10 to the 4, which is that's the temperature of magnesium 2, whether that can exist at large distances and be created in a hot wind. And they concluded that it can, depending on how clustered the feedback model is. So basically the distribution of supernovae in the disk of the galaxy. So my point is that several groups have been working on how you can have cold gas at large distances from galaxies. And I think people are making very good progress on this, even if it's not like fully understood yet. Okay, so sorry, check time. Great. Okay, so conclusions. So we've been studying these compact starburst galaxies at redshift of around 1/2. They have their late stage major mergers and they're massive galaxies. They're very compact. They have these very high star formation rate surface densities approaching Eddington, and these extremely fast winds, 2,000 kilometers per second. And it looks like it's feasible for these winds to be driven by stellar processes, not AGN, which is good because we don't actually see AGN in the galaxies. So one of the conclusions of this talk is just don't forget about stellar feedback in massive galaxies. I think people, when they look at the galaxy stellar mass function, they sort of break it into the high mass part and the low mass part. And for high mass, people think this is where AGN feedback is important. And at low mass, they think this is where stellar feedback is important. And it's not quite that simple, particularly if the galaxies have very high star formation rate surface densities on the massive end. Stellar processes could be quite relevant for quenching star formation. And then for the second part of the talk, in one of these galaxies, we detected this huge O2 outflowing galactic wind reaching well into the circumgalactic medium. The scale is 50 times larger than the stars in the galaxy. So this is direct evidence that outflows do in fact feed the circumgalactic medium. And that gas could have been transported from the galaxy and or cooled out of the hot halo itself. And on smaller scales, meaning 10 kiloparsecs, we detect this multi-phase faster outflow reaching 2,000 kilometers per second. And having a single source with these spatially resolved kinematics and multiple probes of gas at different densities and temperatures should be highly informative for theoretical models of feedback. So this is just one source. We have data on several more, and we have several other papers that should come out on the NERSPEC data, high-res data, KCWI, lots of Keck data in the next several years. Okay, thank you.
Thanks very much, Alison. It was a really wonderful talk. So I think we'll go straight to questions.
I have a question, if that's
Fire away.
So these are, very sort of spectacular cases, which is great. Do you have a sense of, I'm trying to get a sort of broader picture of how outflows might be present in the broader galaxy population at these redshifts. Is there a handle on that?
Yeah, so I think there's 2 points here. One is normal star forming galaxies have outflows. They don't have to have a star burst to have an outflow. But for normal star forming galaxies, the outflow velocities are like 100, 200 kilometers per second. The key thing that you always want to know is the mass outflow rate, and that's really hard to determine because you want to know the density of the electron density in the outflow and the spatial extent, and it's just really hard with absorption line studies to measure those things. So we don't really know that, but my guess is that for normal star forming galaxies that are not star bursts, outflows are definitely relevant for regulating star formation, but probably are not substantial enough to quench star formation. So when you're talking about quenching, then you need a more extreme outflow where you have a lot of gas and you're ejecting it to much larger scales. So, you know, according to theorists, like that's easy to do with AGN, but not so much with stars. So I think these galaxies are important for 2 reasons. One is to show that stellar feedback can be relevant, probably for quenching, but you need, I don't want to call it extreme, but you need high star formation rate surface density. So then the question is like, how, like, are these galaxies just weird, right? Like, how do these galaxies fit into the larger galaxy population? So another paper that we're writing, this is being led by a student of Ryan Hickox's at Dartmouth, is trying to determine the space density of these galaxies and put them, understand, like, so they're not very common. That could be because they're just rare because they're weird, or it could be that they're just short-lived.
Yeah.
So my guess is that part of it is that they're just short-lived. So if we think that most massive galaxies do go through a major merger at some point, maybe it's not that uncommon that they do have a brief stage where they have a really extreme stellar driven wind. So we're still working on that, but I think that's, I used to think these galaxies were just like weird, interesting, extreme sources, but maybe not that relevant for galaxy evolution on the whole. And I'm coming around to thinking that they might be more relevant. Like many galaxies might go through a phase like this.
Yeah, that's sort of what I was getting at. I guess a follow-up question is more for the first part of the talk. If you have these extreme star bursts, you know, at redshifts of 0.5, then I guess they should have you're making a lot of stars in that process and then quenching it, then you'll have a very distinct population that today wouldn't look like a post-starburst, but a maybe post-starburst, but you could still age date them, possibly with good spectra, depending on the number of stars formed in the burst versus the underlying population. I don't know if anybody looked at that.
Yeah, so they should look, morphologically, they should just look like normal ellipticals. But you're right, if you could get a really detailed star formation history, maybe you would see that there was 1 or 2 really strong bursts at some, you know, this like major merger coalescence stage. I don't know a lot about studies like that at low redshift. I mean, I'm trying to think of how long those A-star features stick around for, like how long you could date those. You could see that we could date the starburst of this one really well because of those Balmer absorption features.
Yeah.
And as those fade with time, that's going to be harder to do. So then you just need higher signals.
And there's always ambiguity in reconstructing the star formation history. You know, it could be you know, a trickle of more recent star formation, or it could be a big burst at an intermediate time. And these things are hard to sort out, but I would have thought that you could maybe make some kind of headway on that topic.
Yeah, so to get those spectra that I showed with those strong Balmer absorption features, you had to have a lot of star formation in a relatively short period of time. I do think as galaxies have, over time, they have more mergers and more minor mergers. Some of these signatures might get wiped out spectrally. So maybe there's other ways. I don't know. It's a good question.
Thanks.
And I do think cosmological simulations and looking at how the merger history and the star formation history of galaxies in cosmological simulations is a relevant, helpful pointer here.
Yep. Of course, we hope to find the simulations are wrong and are missing some important piece of physics.
They're generally not quite right. Other questions? Okay, well, I'll throw in a question or two. I had a whole bunch. So, I mean, one, question that came to my mind is where these systems live on the Schmidt-Kennicut relation. So that can tell you something about whether they're weird or just sort of normal, but still weird. It's a blunt tool, but if they lie far off Schmidt-Kennicut, it tells you you've got something that's really wacky, because it's pretty hard to not lie on it. So if you've got ALMA data, I think, then you can get the density of molecular gas and you can play that game. And if you've got it in extended, if you can see it, you can then look at whether there are two versions. There's the, really blunt hammer, which is just taking the whole bit and asking what the galaxy wide is. And then you can look along filaments and so on. And we played some of that game here. Have you tried that or checked it out?
No, that's a really good
density
question.
One thing, and then showed it was Eddington Limited, which I thought, geez, wow, that's wild. But then, I would think they'd be way off Schmidt-Kennicut then.
Yeah, that's a really, really good question. And no one's asked about that before, and I hadn't thought about it. The radio data has been hard to get, this, and it's just slow. So we get like one galaxy at a time. Like every couple of years, we get like one more source. So we published.
That means you're ahead of the curve.
Yeah, it's so painful.
Yep.
So we published, I think, 3 sources. We have data on a handful more. So maybe we have like the minimum sample size now that we could look at that. That's a really good question. And I don't recall us ever making a plot like that. So I'm going to take that question back to Jim Geach. Yeah, that's a really good question.
And also looking at it in 21 centimeter, if you can do that in these, do they have, what is the CO to H1 ratio? There's all these interesting questions, because in Schmidt-Kennicut, it's the sum of the two systems that we played with here. They're CO dominated. But the other question I had, you mentioned radio. What about continuum? Is there radio continuum above what you'd expect from the starburst? Or there lobes, anything like that?
Good question. So yeah, okay. So for the longest time, we've wanted better star formation rate estimates. We were not thrilled with the uncertainties on the star formation rates that we had from the infrared data. So we got radio continuum data to try to get a better handle on the star formation rate. And what we found was that roughly half of the galaxies lie on the infrared radio relation, and roughly half of them do not.
Above or below?
The radio is low. The radio is low for the infrared. So we actually have a paper on this. Grayson Potter is the first author, and Christy and I and others are on. I can send you the link. That just came out, or it's in the, no, I think it was just accepted. So yeah, this is like very, very recent. So it's not clear what's going on there. There's a few possibilities. One, it's possible that the infrared is high, but I think we kind of came around to, we think that it's probably that the radio is low. And it wasn't clear if it was like absorption from synchrotron, or if it was like the time scales the time scale that the radio probes. These galaxies are not just forming stars at a constant rate. They have, they're in the starburst phase. Some of them are probably like becoming post starburst. Like they've had a very non-steady star formation history.
I think the radio is sensitive to the supernova rate. So I think that's primarily what drives it. So you could just be in a valley there. But the other thing is it puts a hammer on the AGN thing again if you don't have lobes, which is really weird.
Yeah,
because
we don't. That's right. So yeah, so we did not see, only one of the sources did the radio look like it was coming from an AGN, and the others it wasn't.
Right.
So yeah, these have weird radio.
No, it's weird. It's if the star formation is just chewing up the gas before it ever gets to the hole, which is pretty interesting, actually.
Yeah, so this is something that we've been really kind of stumped about for a long time now, which is like, why do we not see AGN in these? These are massive galaxies. They must have very massive black holes, but they're not on. So they must have been on, and they're just not now. So maybe we're seeing them just to sort of play with people. I started calling these pre-post starbursts because I think they're like late, they're like right at the end of the starburst, like just, you know, about to become post starburst. And it's possible that by the time the galaxies get to that stage, yeah, there's not a lot of gas right at the very, very center. That's my guess, but that's just complete speculation. It's pretty weird that we don't see more AGN activity. These do have dust, so it's possible that they're just like really, really obscured.
Right.
Yeah.
Are there other questions? I don't want to.
Still been bugging for a long time.
Yeah,
Like,
we should chat about that offline, because that's really weird and interesting at the same time. Other questions? Just pipe in, shout.
Just a quick question. A couple of mechanisms were proposed for or described for driving the gas at those high velocities. Would the spectra not show more metals in them than is perhaps the case if it was driven by supernova activity?
So the metallicities look like they're high.
Oh, they do. Okay.
Yeah. We have, you can use optical line ratios to constrain metallicities, but you want to correct for dust. And we don't feel like we have a good enough handle on the dust to, at the moment, to make those corrections. So I can't quote you metallicities, but they're definitely in like the high metallicity part of optical line ratio diagnostic diagram. So these are high metallicity.
Right. Okay. Thanks.
Yeah, that's a good question.
Any other questions? I have one more, if I could get it in before we let you go. How do you really know when you got a mission line gas, whether it's on the way in or on the way out?
Oh, from the, well, so from the kinematics relative to the lines in the galaxy. So from the stellar spectrum, you can get the redshift of the stars. From the emission, usually, I'm not sure if I'm reversed for you, so I'm not sure which way it should be, but basically there's like a narrow line and then a broader bump, right? So the narrow line, that redshift matches up with the absorption redshift from the stars. So that's the redshift of the stars and the gas in the galaxy. And then you see this additional component that's either blue shifted or red shifted. So if it's red shifted, it has to be gas on the near side. These galaxies have enough dust. You just shouldn't be seeing, except, sorry, for the, so yeah, exactly. You tend to, you're seeing gas.
Sure that you're not seeing gas on the other side of the galaxy. That's the key.
Except for that large, that like 100 kiloparsec outflow, there, that scale is larger than the galaxy. So there we are seeing gas on both sides. And there you actually can see both blue shifted and red shifted.
I see.
Gas in emission.
But
the smaller scale one, you just see the blue shifted side because it's in front of the galaxy.
And there's so much garbage in the galaxy that there's no way you would see emission from gas coming in on the other side.
Yeah.
Oh.
Yeah, but we do actually see some redshifted as well for the larger, slower outflow.
Okay.
Yeah.
Any other burning questions before we let Alison run off to the beach?
I wish.
We're gonna go shovel snow. So
that though about the radio data.
Yeah, we should chat about that at some point. I think I owe you an email. So anyway, can we thank Alison again? That was a really wonderful talk. I've got more questions than answers now, and that's always a sign of a good talk for me. So let's thank her again.
Thank you. I appreciate it.
Thank you.
And a virtual pizza, to you, which is normally what we do if you were here. So
fabulous. I'll have